Hey everyone, apology to start off. I let my AirPods die out, so the volume might not be great for today, but hopefully this is still helpful. So we are going to try to graph a rational function defined by y is equal to x plus 3 all over x squared plus 4x plus 3, right? So first things first, let's factor our denominator and see if we can simplify anything. So if we go ahead and try to do that, we'll end up with x plus 3 over this quadratic factors as x plus 3, x plus 1, that's terribly written, x plus 3 bracket x plus 1. And right away, we know that we can cancel a factor out, namely the factor of x plus 3, right? And so our function simplifies down to 1 over x plus 1, but we remind ourselves that whenever we cancel out a factor like this in a rational function, this doesn't completely disappear. It makes the x-intercept at x being negative 3 disappear. It makes the vertical asymptote at x equals negative 3 disappear, but it gives rise to a point of discontinuity, okay? So this entire rational function is going to behave like this simplified function with a point of discontinuity, or if you'd rather, a hole in the graph, an open hole in the graph, where the x-intercept used to be, right? Well, where this factor gets canceled out. That's when x is equal to negative 3. And since this is a point of discontinuity, after all, it must have coordinates. And so to find the coordinates of that point, it's no longer an x-intercept, as it were, if we had not been able to cancel out the factor of x plus 3, but rather we have to plug in this value of x equals negative 3, i.e. the root that would have been before this factor canceled out, into our new simplified function. And so y is then equal to 1 over x plus 1 means negative 3 plus 1, which means y is equal to 1 over negative 2, and so y is negative 1 over 2, meaning that we have a point of discontinuity at x being negative 3, y being negative 1 over 2, okay? So now we can go back to our simplified function of 1 over x plus 1, and we can still get some information out of this piece. Now, the numerator is just 1, right? It's static value of 1, so we're never going to have that be equal to 0, meaning we're never going to have an x-intercept, right? We are not going to have an x-intercept. Now, this is a simple 1 over x function with a simple, again, with a horizontal translation of 1 to the left, right? So we're still going to see the same horizontal asymptote, which you can imagine as the limit as x goes to positive infinity and negative infinity of 1 over x, right? As x gets really, really big, i.e. close to infinity, 1 over some gigantic number is basically 0, right? 1 over some gigantic number plus 1 is still basically 0. And so from the 1 over x plus 1 function, we still get the fact that we have a horizontal asymptote along the line y is equal to 0, and we have a vertical asymptote along the line. Vertical asymptotes are created by a denominator of 0, and what value of x would make our denominator be equal to 0? Clearly that's negative 1, right? When x plus 1 is equal to 0, and so x is equal to negative 1. That's our vertical asymptote, and so we can start putting some parts of our graph together. X being negative 1 gives rise to a vertical asymptote. Y being equal to 0, that's our beloved x-axis, right? Y is equal to 0 is our horizontal asymptote. And we're not going to have an oblique asymptote because oblique asymptotes are only when the degree of our numerator is greater than our denominator, and we have the exact opposite in this case. Now, we know we have a point of discontinuity. We actually found that point, right? We found its coordinates. That's going to be at negative 3 and negative 1 over 2. So that's around here. There's a black marker here, right? That's around here at negative 3 and negative 1 over 2. Now, we have our asymptotes, so we know what this is roughly going to look like. We know that this is going to look a lot like the graph of 1 over x. Right? This is very, very close to the graph of 1 over x. The only thing we're observing is a horizontal translation of -1, right? So really, it's gonna look exactly the same as the graph of 1 over x, just shifted 1 over to the left, right? So if you are familiar with your 1 over x graph, you know that there's typically a point at 1 and 1, so another point is gonna be shifted 1 to the left at 0 and 1, right? 0, 1. Conversely, we could also get that by finding the y-intercept, right? We could have found our y-intercept from the get-go by either plugging in x equals 0 into the original or even into the simplified, right? Either or, plugging in x equals 0 gives us either 3 over 3 or 1 over 1, and so our y-intercept is at x equals 0, y is equal to 1, right? That's easy enough to get. And these functions, these 1 over x kind of functions in that family of functions, they're symmetrical, right? And so if we have a point at 0, 1, that's over 1 up 1, we get the same thing in the other quadrant, in the reflected quadrant down here in quadrant 3, and so that's 1 over and 1 down now. So we're gonna be at -2 and -1, okay? I'm gonna try to squeeze that in here. -2 and -1, right? And this, I'll remind you, is our point of discontinuity, so it has to be an open circle, because it's not defined at this value, right? Even though the function acts like it crosses through that point, we know that our function is not defined when x is -3, right? Plugging in x equals -3 in the original y function would produce a denominator of 0, which is obviously undefined, and so we get a nice open point at -3, -1/2. And so now we can start drawing out the general shape of 1 over x graph. Knowing what 1 over x typically looks like, we can apply here with a very simple transformation. And so we know it looks something like this, right? And it tapers off just above our horizontal asymptote, and likewise in quadrant 3, and it hugs our asymptotes as y approaches -infinity down there. And we have our point of discontinuity. We have our horizontal asymptote y equals 0. We have our vertical asymptote at x equals -1. We have our point of discontinuity, -3, -1/2. We have a point in both pieces of the graph. And so I would consider this a good enough sketch of the function we were given. So I hope this helps. I hope you guys can start to see patterns in the way that these rational functions tend to behave, whether the numerator or the denominator has the higher degree or they have the same degree, right? How the vertical asymptotes, horizontal asymptotes all kind of start to take shape, and how we often see a lot of symmetry with these rational functions. And the more you practice, obviously, the faster you'll see those start to pop out of the graphs. Okay. Again, hope this helps. If you guys have any questions, comments, suggestions, please leave a comment below. I'm happy to do more videos or to clarify anything that might have been a little bit fuzzy. And thanks for watching.